Hello, so today we are going to do this problem called how many numbers are smaller than current numbers. So what we have is an array of numbers, and for each number we want to find out how many numbers in the array are smaller than it. So each number I, you have to count the number of valid g's such that g is different than I. And so basically we have an array of numbers, and for each number we want to find out how many numbers in the array are smaller. That is each number of I, you have to count the number of valid j's such that j is different than I, and number at position j is smaller than number at position I, and we want to return the answer in the inner. So for example we have this, and the output should be this, because we have 4 smaller numbers than 8 here. We have 1 smaller than 1. No, we don't have any. It does not exist any smaller number than it, so we should return 1. Oh, 0, yeah. For 2 we have 1 is smaller than it. But it's not after it. It just has to be different. Doesn't need to be after it. For 2 we have same thing. This one is smaller, so 1, 3 is same. Okay, so we can do this just in 2 loops. This is the easier brute force solution. So that would be something like so it would be in the range of the length of numbers, and a similar thing for numbers here, and from there we can just check if j is smaller than for I. We will need to have our result array here, and we'll need to count. So we can count them like this, and if we find 1 we should just increase, and we could say res of I is equal to count, and at the end just return that. We should do append actually, so it would be something like this instead. Okay, looks good. Submit. Okay, so that passes. This is oven square time. We should think about making this better. So basically we need a way, given a number, to determine all those that are smaller than it. Hopefully in less than oven time. So if we had the array sorted, maybe by just looking at the position we could, just looking at the position will tell us how many numbers are smaller than it, right? So we could have something like this, like sorted, and we could just put the array sorted, and then from there we could just find the count by binary searching on the sorted array. So that would be using bisect here. And so the way bisect work is that, let's just grab this example. So if we take this one, oh, actually this is the numbers one, and then we could just have sorted numbers be equal to sorted for nums. So if we do this, what does, so we have that. Now if we look for, let's say 3, so if we look for, so if we use bisect, let's first import it. We need to pass first the array and then the value. So the array is sorted nums, of course. And then the value we are looking for, let's say, is 3. So we get 4. So we get the index after its presence, right? So this tells us that do we have any guarantee that the array doesn't contain duplicate values? So even if there were like duplicates, we only want smaller, right? So this means that we should probably here have bisect left, because what if I had let's take an array that has duplicates, right? So if we bisect left gives us 3, and just bisect will give us 5, so it will give us after all those 3. So what we want is really bisect left. So bisect left gives us exactly the number of elements smaller than it. So this is what we want, so we could use that here. And we need to pass the number at position I. And we could just, basically that's the count that we are looking for, right? Okay, so this works. In terms of time, this is O(n) log n, and this is O(n), and this is log n, O(n) log n. So overall, it's the total time is O(n) log n. In terms of space, it's we are using this extra array here, so it's O(n) space. Yeah, and that's pretty much it, I think, for this problem. We could check what other people, how other people handle it, but it should be similar. So here we count the occurrence of each number, and then take the running sum of these occurrences. And for each number, it's, okay, that's clever. For each number, it's the running sum of the previous number before it, right? And since we have, according to the problem, we have at most 100, a number is at most 100. So that would mean basically what we can do here is something like this, where we could have count of so this would be just 0 for the range of 101, right? So the max number we could have. And then we could, just for each number, so for num in numbers, we could say count of num is equal to, just increase it, right? So actually here, instead of doing this, we could do that, but we could also just use a collection, right? But let's just keep it this way. And from that, we could say, okay, for just keep a running sum now with them. So it would be plus count of num minus 1. And then for every number in this, so we'd have res here. Minus 1, those are the elements smaller than it, and then we can just return that. Yeah, so it's not nums, it's nums of I here. So this is length of what if we just keep track of all? Yeah, for 0 it would be -1, so that would be problematic. Yeah, so if the number is equal to 0, we want to handle it differently, because otherwise we'll get -1 and we'll get the last element. So if the number is equal to 0, we want to just return append. Okay, so that passes, cool. Yeah, so the solution that I did earlier, which was this one here, with binary search, we could actually just look up the index, and if it doesn't exist, then we will get the index we are looking for. So this one here, we can change it slightly, because instead of returning, so here we could just take sorted number and just look for the index for nums of I. And actually we could just make this num and get the index for that element, and then that would be the result that we are looking for. So we could just do it like this, and we could even use just a list comprehension here. Okay, so we could just use a list comprehension like this, where here what we want to return is mostly this. We can get rid of this, and except here we need the sorted numbers, so we could just say sorted nums. Okay, so that works. Yeah, so that's it for this problem. Thanks for watching, and see you on the next one.